Section 4.2 is going to come in two parts. This part's going to be all theory and definitions. So there's a girl throwing up words because that's how you're going to feel by the end of this section. And then in the next section, we'll learn computation techniques. So in many textbooks, you will see a mass spring oscillator system where you've got an object and it's got certain forces acting on it. And you might say, well, that's not very exciting. But what happens is you get this general second order differential equation, linear, and that one equation can be used to model many real-world phenomena. For example, vehicle suspension, a swinging door, any musical instrument like beating of a drum, RCL circuits. So we're going to get a lot out of that one equation. We're going to spend actually a whole chapter solving this differential equation. So let's talk about the categories of motion. There are two types: free vibration, which we're going to look at more closely in a minute, and then forced motion. Forced is any time F external is not zero. And resonance is when the waves are reinforcing each other. And so sometimes you'll want resonance and sometimes you won't. When you're pushing a child on a swing, you want resonance because you want to push at that exact moment that you're going to give the child the most boost, right? If you push at the wrong moment, they're just going to fall right off the swing. Sometimes you don't want resonance. You don't want those waves to reinforce each other. And for a long time, the Tacoma Bridge in Washington was thought to be an example of resonance. It turns out it's actually aeroelastic flutter, but it's such an exciting video. Let's look at it anyway. This was about 1940, and here's the bridge. And then it started shaking like this, crazy. And then I think we're going to see some people trying to walk over it, very brave souls. Or perhaps they were stuck halfway through when it started doing this. I'm not exactly sure. I have it sped up. I have it on twice speed. I think in a minute we're going to see it collapse. There it goes. All right, back to our lecture. So that's a case where obviously you wouldn't want resonance, but that wasn't resonance anyway. Free vibration. Free vibration comes in three categories. Don't worry too much about the names of the categories. There's undamped motion, and I've drawn a picture of each, and you can really see why they're named what they are by looking at the solutions. Undamped motion is going to go on forever. Imagine a swinging screen door with no damping on it. It's just going to oscillate back and forth forever. That would be undesirable, right? You wouldn't want your door to swing all day back and forth. So it's going to have cosines and sines in the solution typically. Underdamped motion will have cosines and sines, but then there'll be an exponential term. And so as t goes to infinity, that exponential term is going to damp the motion because the e to the negative t is eventually going to go to zero. And so if this is a screen door, it's going to swing a few times and then stop swinging. And then critically damped or overdamped motion will have no cosine, no sine. It'll be exponential terms only. RCL circuits are an example of this mass spring oscillator system. I just want to show you. Here's our mass spring oscillator equation. Here's the equation governing an RCL circuit. The inductance plays the role of the mass. The resistance plays the role of the friction. And then the capacitance plays the role of the spring constant. So today we're going to go through a bunch of theory related to this basic differential equation. So first things first, existence and uniqueness. Yes, there's another existence and uniqueness theorem. You don't have to memorize this, but it says that if you have this linear second order differential equation, it will have a unique solution on an interval where all of the coefficients are continuous. Now, I've written this in monic form. Monic, it's a fancy word for any polynomial whose leading coefficient is 1. So this is monic. Let's apply this to an example down here. If we've got this differential equation with these initial conditions, first of all, is that linear? Yes, it is. So it follows the rules of this EUT. Find the largest interval on which theorem 1 guarantees a unique solution to the IVP. So the first thing we need to do is get it in the right form. We need to divide through by t, so it's a monic polynomial. So we get y double prime plus y prime plus 1 over ty equals 0. So my p of t is the coefficient of y prime, that's 1. My q of t is the coefficient of y, that's 1 over t. And my f of t is 0. So this guy is continuous for all t. No problems there. Same with this guy. This guy is not. This guy's continuous on any t not equal to 0. So you can go from negative infinity to 0, or you can go from 0 to infinity. Now, we have to choose. We have to choose which interval we want. So then we go up to the initial conditions. The initial conditions are given at t equal to -1. IC at t equal -1. So we look at these intervals and say, okay, which one contains t equal -1? Well, the first one. So the theorem guarantees a unique solution on that interval. Okay, homogeneous versus non-homogeneous. A homogeneous differential equation, or in math, basically homogeneous gets overused, but in this case, it's where you're driving, your f external is 0. So you have a differential equation and you set it equal to 0. So that's homogeneous, and here's an example. Non-homogeneous f exterior is not 0. Now for every non-homogeneous, such as this one, we can look at the associated homogeneous, this one, by removing this external force and replacing it with 0. It turns out that solutions to the non-homogeneous are very closely related to solutions of the homogeneous. So we're going to spend the next 2 sections working on solutions to the homogeneous. So I'll talk more about solutions, how solutions to the non-homogeneous are related to solutions to the homogeneous towards the end of this lecture. But now I'm going to jump to another topic. I know this seems just kind of crazy, like they're unrelated things, but actually they're not. The superposition principle. Now that we know what homogeneous equations are, we can talk about superposition. There's a superposition principle for homogeneous equations and for non-homogeneous. The non-homogeneous is much harder. We'll talk about that later. But the one for homogeneous is very simple. It says if you have 2 solutions of a second order homogeneous linear differential equation, then any combination of the forms c1y1 plus c2y2 is also a solution. So I have a proof at the end, but I think it's easier to see with an example. So I've got a homogeneous linear second order differential equation here, y double prime plus y equals 0. I'm stating as a fact that cosine t and sine t are both solutions. Now I'm stating that, but you could easily check it. So we've got 2 solutions. We're going to verify that any linear combination of this form is also a solution. All right, so in order to verify that, we have to compute y prime because we need y double prime, and we can't get to y double prime unless we go through y prime. So I computed y prime and I computed y double prime, and now I'm going to look at this differential equation. It's got a left-hand side and it's got a right-hand side. I'm not going to assume what I'm trying to show. I'm going to compute the left-hand side and the right-hand side separately. The left-hand side is y double prime plus y. So that's negative c1 cos t minus c2 sine t. And then I'm going to add on y, which is c1 cosine t plus c2 sine t. Then I simplify and I say, oh, these terms cancel and these terms cancel, and I get 0. The right-hand side is 0. So the left-hand side equals the right-hand side. So indeed, I do have a solution. When I take 2 solutions, I can multiply by any constant, and then I can add those together, and I still have a solution. Okay, assuming that all solutions look like that, which is a big assumption, find the unique solution to the IVP given by these facts here. And it's unique because of the existence and uniqueness theorem. So I've got y and I've got y prime. I need to use these 2 facts. Y of pi over 4 is 0, and y prime of pi over 4 is 1 over root 2. So my first equation becomes 0 equals c1 cosine pi over 4 plus c2 sine pi over 4. And my second equation becomes 1 over root 2 is negative c1 sine pi over 4 plus c2 cosine pi over 4. Okay, well, what does that give me? It gives me 0 equals c1 times 1 over root 2 plus c2 times 1 over root 2. And then 1 over root 2 equals negative c1 1 over root 2 plus c2 1 over root 2. Now what I'm going to do is multiply both of these equations by 1 over root 2 to clean them up. The first one is 0 equals C1 plus C2. And the second equation gives me 1 equals negative C1 plus C2. That's better. Now I'm going to add those two equations to get 1 equals 2C2. So now I'm going to move over here. So I've got C2 is a half. Now I put that back into either equation to get C1, and I see quickly that C1 is negative 1/2. So my unique solution to the IVP is y equals, I'm going to take those values and plug them into my equation for y, negative 1/2 cos t plus 1/2 sine t. Okay, if you have two solutions to a second order homogeneous linear differential equation, and you can write all solutions as a linear combination of those two solutions, we say that you have the general solution. And in that case, the other ways of saying that, and it's a little confusing because there are many ways of saying the same thing, is that y1 and y2 form a fundamental set. And another way of saying that is y1 and y2 are linearly independent. Okay, so a big question is, if you have two solutions, y1 and y2, of a second order homogeneous linear differential equation, when do you know that C1y1 plus C2y2 forms the general solution? And to answer that, first we need to define what a Wronskian is. So if you have two solutions, y1 and y2, the Wronskian of those two solutions is the determinant of this matrix. It's this right here. Those straight bars mean determinant. And how you compute a determinant is you take the product on the main diagonal, y1, y2 prime, and you subtract the product on the non-main diagonal, y2, y1 prime. So let's find a couple of Wronskians. For this one, W is, I put cos t, sine t on top, and their derivatives on the bottom. And I get cosine squared t minus negative sine squared t, which is cosine squared t plus sine squared t, which is 1. Now, if you were to switch the labels, if you let y1 equal sine t and y2 equal cosine t, you should verify that the Wronskian will change, but it will only change by a minus sign. You should verify the Wronskian is negative 1. Okay, let's find this Wronskian, e to the negative 2t, 2e to the negative 2t, negative 2e to the negative 2t, negative 4e to the negative 2t. All right, and now we take the determinant, that's negative 4e to the negative 4t, and then I'm going to subtract a negative, so it would be minus negative 4e to the negative 4t, which is 0. All right, here's the big theorem. You have two solutions of a second order linear homogeneous differential equation. Then C1y1 plus C2y2 is the general solution if and only if the Wronskian is not 0. So in the example we did with cosine t and sine t, since the Wronskian of y1 and y2 was equal to 1, which is non-zero, indeed the general solution was this. Okay, and you can read through the rest of that page. Let's jump to the last notion of the day, which is how the non-homogeneous solutions are related to the homogeneous solutions. So suppose you have non-homogeneous equation like this. You go ahead and you find a fundamental set for the homogeneous equations. You replace the f of t with 0 and find two solutions that form a fundamental set for the homogeneous associated DE. Then any general solution of the non-homogeneous is going to be a particular solution of the non-homogeneous. So you just find any particular solution, and then you add on the general solution to the homogeneous. And so it turns out that finding general solutions of non-homogeneous relies heavily on this box right here. So we're going to spend quite a bit of time on this box. This is going to be sections 4.2, the other part of 4.2, and 4.3. And then we'll talk about finding particular solutions in section 4.4 through 4.6. And this theorem will make a lot more sense once we get to section 4.4 through 4.6. Okay, and that is the end of this section.